All right, so let's take a look at a combination of two atoms, a metal and a nonmetal. Okay. Um, you want to do tungsten? Why do you want to do tungsten? What's so special about tungsten? All right. All right. Well, tungsten's a little bit complex. All right. Um, why, are you a Wofford fan or something? No. Okay. No, well, I don't mind doing with tungsten. I'm just saying. All right. So tungsten then, in its valence level, is going to have two s electrons represented by the placement of cesium and barium here, and then four d sublevel electrons. Okay. In addition to that, it's got all these electrons. Those aren't really in the valence level. Technically, if you're just looking at tungsten that's in its ground state, you really only have two valence electrons, because only the s orbital electrons and the p orbital electrons are considered the valence level unless you're using them in bonding. Now the tricky thing about all these metals here in this region we call the intertransition metals is that the d sublevel electrons, which are in a lower energy level, so these electrons represented by these two atoms here are in the 1, 2, 3, 4, 5, 6th primary energy level. And then we drop back one primary level for these d sublevel electrons, all right? Well, we can actually use those in bonding, and that's what makes it so tricky to pick out what their actual oxidation number is. Now, the elements that are in this first column here, those almost always have an oxidation number of 3 plus, because they can use that d sublevel electron in bonding, okay? So when we think about it, we think of lanthanum, for example, as having only a valence level set of electrons of 2, but it can use this third one in bonding, so it actually ends up with a 3 plus oxidation number. So that's a little beyond where we discussed it in this class, but that's where you get that from. That's why all the elements in this column here have a 3 plus charge. In fact, in reality, the d sublevel electron here is actually further out from the nucleus than these s sublevel electrons. But as we go across the row, these electrons start to drop back inside the s sublevel electrons. Okay, so there's some flexibility there based on the number of electrons in that d sublevel. Remember, the more electrons you have in the same primary energy level, the tighter the nucleus pulls on those electrons. Okay, it's called the shielding effect. Okay, and that's why that happens. And that's why you get all this range of different oxidation numbers for all these transition metals. And it's so hard to predict what's going on. So, there are a few that you're supposed to know, like iron has a 3 plus and a 2 plus charge, and nickel has a 1 plus and a 2 plus, copper has a 1 plus and a 2 plus charge, okay? Possible. All right, so going to tungsten then, we need to figure out which one of all these, I think it's got 5 different oxidation numbers it can have. Okay, which one are we going to use? All right? So you can look on the set of homework references I gave you, and there is a periodic table that shows all the common oxidation numbers. Doesn't mean there aren't more, just means those are the common ones. And the ones in the boxes are the most common of those common ones. Well, I'll take that back. Tungsten only shows 2. 6 plus problem. That's used here. Subelectrons. D sublevel. That can do something. Doesn't really give it up. You give up 4, but not really 6. It's kind of tricky. Okay? Don't sweat it. We don't need to worry about it too much. But let's just say, since tungsten common on 6 plus, it's given up all 6 of the electrons in its s sublevel and the d sublevel. Okay? The s sublevel in, what did I say that was? 7, 6. And the d sublevel will be in 5. Okay? And we're going to put it together, let's just say, with chlorine. All right? Well, chlorine has a 1 negative oxidation number when it's in a binary compound. Binary compounds have only 2 elements. You can have more than 2 atoms in the formula, but it only has 2 elements, okay? A 1 negative charge. Okay? So the way we get those together so the charges all equal out is to have 6 chlorines, and that neutralizes this 6 plus charge. And so tungsten 6, Roman numeral 6, we're naming it. This is tungsten 6. Okay, and we're going to name this chlorine chloride because negatively charged monoatomic ions have an IDE ending, and the formula is WCl6. Tungsten 6 chloride has this formula.